Welcome to the video lecture for Experiment 8, Molecular pH Probe. pH is very important in chemistry, as many rates of reactions depend very strongly on pH. You have measured pH in laboratories before, often using a pH meter. While this is a very simple and straightforward technique, pH meters are not always practical. For example, how do we measure pH inside of a cell, or in a cloud, or at the surface of titanium dioxide? Clearly, a pH meter is not going to work for these measurements. It is much too large to fit inside a cell or in a cloud droplet, and it is entirely the wrong shape to measure pH at a surface. Molecules do not have these constraints, though. So a molecular pH probe, such as acridine, can easily fit inside of a cell or in a cloud droplet, and it can also sit on top of a surface. Molecular pH probes are molecules, weak acids or bases, that exhibit different spectral behavior depending on whether they are in a neutral or ionic form. Since we can detect their presence spectroscopically, we are not limited to bulky physical probes. We can insert this molecule into our medium of interest, be that an aqueous solution or a blood cell or a cloud, and use spectroscopy such as UV-vis absorption or fluorescence spectroscopy to detect them. This allows us to measure pH in many complex systems. As discussed before, acridine can exist in two forms, in its neutral form or in a protonated form. So at different pHs, we will have different amounts of the protonated and neutral form present. The fluorescence spectra of the neutral and ionic form of acridine are different. They have maximum intensity at different wavelengths. So at low pH, acridine is primarily in its ionic form, and its fluorescence is redshifted compared to that of the neutral form, which we see primarily at higher pH. We can use acridine or other molecular pH probes to determine pH by measuring the ratio of absorbance or fluorescence intensity at the peaks of emission or absorbance of the two different forms. So in this case, that would be at approximately 425 nanometers for the neutral form and 475 nanometers for the ionic form. At low pH, we are going to get a very low ratio, since acridine is primarily in its ionic form, and fluorescence that we see will be from the ionic form. So we can mark off an X on our plot on the right-hand side where we are measuring the intensity ratio of the neutral to ionic form versus pH. Conversely, at high pH, we will have a much larger ratio, since acridine's fluorescence is primarily due to the neutral form. Near acridine's pKa, in more neutral environments, at more neutral pH, we will see emission from both the neutral and the ionic form. And the ratio of intensity that we measure will be in between that of the ratio that we measure at low and high pH. Now, even right at a molecular probe's pKa, although we expect to see equal concentrations of the neutral and ionic form, we do not necessarily expect the ratio of intensity to equal 1. This is because either the ionic or neutral form of the molecule may absorb more strongly or emit more strongly. Now, looking at the graph on the right-hand side, we can imagine drawing a straight line through the points that we have to get a linear calibration curve for pH. This would not be an accurate calibration curve, however. as you measure numerous pHs in the lab, what you will see is that at low pHs, there will be no change in the ratio that you measure, even as you increase the pH. Likewise, when we start off at a very high pH and decrease it, you will also see no change in the intensity ratio. This is because when we are far enough away from the pKa of our molecule, that molecule exists almost completely in either the ionic or neutral form, depending on whether we are at low or high pH. However, near the pKa of the molecule, you will see a dramatic change in the intensity ratio as the pH changes, which will result in a curve that looks like this. And this looks exactly like what you would expect from a pH titration curve. Now, once you have a curve that looks like this, you could take a solution of unknown pH, measure an absorption or fluorescence spectrum, and use the intensity ratio of your molecular pH probe to determine the pH of your solution. Now, this is only going to work, though, in a certain pH range that is centered around the pKa of your molecule. You can only use this probe where we have a slope that is non-zero. So at pHs that are much below or much above the pKa of your molecular pH probe won't work. So this brings me to my next point, which is why would we pick one molecular pH probe over another? In this week's lab, you are looking at two different pH probes, acridine and bromothymol blue. There are several reasons that might lead you to pick one molecular pH probe over another. The first is the pH range. As mentioned before, molecular pH probes are only useful in a narrow pH range centered around the molecule's pKa. So, if we have a curve that looks like this for one molecule, we can see that only in the region where the slope is non-zero will it be useful. Another molecule may have a different pKa and may have a slope or a curve that looks like this. So we can see that the pH range in which both of these molecules are going to be useful is very different. So depending on the pH of your system, you would choose a different pH probe. The next 2 points, instrument availability and sensitivity, are somewhat related. You will be looking at two different molecules, one of which you will use UV-vis spectroscopy and one of which you will use fluorescence spectroscopy. Fluorescence is a much more sensitive technique than absorption. So that means that you do not need a very high concentration of your fluorescent pH probe, whereas you might need a much higher concentration of a pH probe that works with absorption spectroscopy. So in many cases, this will make fluorescing pH probes more useful than pH probes that do not fluoresce. However, fluorimeters are much more expensive than absorption spectrometers and may not be as readily available, in which case you would use a molecular pH probe that does not fluoresce. There are many other considerations. For example, experimental artifacts can be introduced by other solutes in solution. So, as an example, if we were looking at a pH probe that works via absorption spectroscopy, we know the absorption spectrum of our molecular probe, but in our complex system, we are not only going to have our molecular probe. We will have other species that may absorb light, and they may absorb light at the exact same wavelength as our probe molecule. So I'm calling this orange trace an absorption spectrum of an interfering solute. And it is interfering because its absorption overlaps with that of our probe molecules. So when we measure a spectrum in our solution, we are not going to see distinct peaks for our pH probe and for our interfering solute. Instead, we will see a single spectrum that will be a combination of the two. So it may look something like this. Now, when we measure our pH ratio, you can see that it is different than what we would measure if the interfering solute were not there. And when we plot our ratio on our graph, the pH that we would infer from our measurement is going to be different than the correct pH because of this solute. So to get around this problem, we could use a different pH probe that absorbs at different wavelengths, where there is no interference from the interfering solute. So in this case, if we used our pH probe that had the green absorption trace, we would not have to worry about the solute when measuring pH. The two pH probes that you will be using in this week's lab use ratios. So, as we've gone over, we use molecules that have different absorption or emission spectra at high and low pH, and as we vary the pH, the ratios of their intensities change, and this is how we obtain the pH curves that we are looking for. Most pH probes do not actually work on this principle. It is much more common for a molecular pH probe to show different intensities at different pHs. So, for example, the fluorescence intensity of a pH probe may be very high at high pH, but very low at low pH. So rather than looking at a ratio of intensity at different wavelengths, we could simply measure fluorescence intensity, and as we went from low to high pH, that intensity would increase. So we could plot fluorescence intensity versus pH and get a curve that looks just like the one that we'd see by measuring ratios. Measuring overall intensity is much more straightforward than measuring intensity ratios. I much prefer using molecular probes that have wavelength shifts and that rely on ratios, however. This is because it reduces the risk of experimental artifacts. For example, in a complex system, as we discussed before, you are not only going to have your pH probe, you will have other solutes that are present, and that might affect your measurements. So for example, what if we have high pH, but we have molecules in our solution that quench fluorescence from our pH probe? Well, we are going to get lower intensity because of the quenchers that are present. So if we are measuring only absolute intensity, the pH that we infer from our measurements is going to be lower than the actual pH because of the presence of the quencher. Given the same circumstances, if we have a pH probe that has a wavelength shift rather than a shift in intensity, we will once again see much lower intensity at high pH in the presence of the quencher. Once again, the red trace is much lower in intensity than the purple trace, even though the pH is the same. However, the ratio of peaks at the two wavelengths of interest is not going to change, so the pH that we measure will still be correct, even though the overall intensity is lower. After this week's lab, I hope that you will be more confident using UV-Vis and fluorescence spectroscopy, which are very useful analytical techniques. I hope you'll be more comfortable with pKa and pH. The pH curves that you create will be used later in the semester during the lab exam to determine the pH of unknown solutions. So this will come in handy for you. I hope that you will gain an appreciation of molecular probes, and that as you write your lab reports, you will think about when you would use molecular pH probes rather than pH meters, and when you might choose one pH probe over another. So with that, I will leave you, and I will see you next week.